Today we're going to talk about torque. We're going to define torque. You've already done a torque activity, and I want to go over that first. For those people that are absent, they'll know what we did. So anyway, here's what we did, and I'll zoom in on this. Well, I'll use the picture I drew first. We took a meter stick, and we made sure that it stayed upright. Somebody could hold it right at the bottom so it wouldn't, flop around. And then somebody pulled it horizontally to the left with the force F1 at a distance R1 from the bottom of the stick. Now, the stick, if that's all you did, the stick would fall over. But to keep the stick standing straight up, we pulled with the force F2. And we found that F2 had to be bigger than F1 to keep the stick from falling over, to keep the stick standing straight up. So F1 does not equal F2. There is another horizontal force, and that's the force of the person that was gripping that meter stick at the bottom to keep it from sliding off the table. And so what we did was I told the students to put R1 0.9 meters up the stick, and then put F2 would be 0.4 meters up the stick, or 40 centimeters up the stick, and then pull on it horizontally, one to the left, one to the right, and measure the forces. Okay? Now I'm going to use one of the group's notebook results and show you what they got. So they redrew the picture. Now I'm going to zoom in on these data here. Now, at the very top, there, F1, they measured it to be 1.5 newtons. When F1 was 1.5 newtons, what was F2? Well, they got 3.3 newtons. So more than twice as big. But then we multiplied. I told you to multiply the distance from the bottom of the stick to where the force was applied to the force at that point. So R1 times F1, 0.9 times 1.5 is 1.35 Newton meters. And for F2, they measured 3.3, so you go 0.4 meters times 3.3, you get 1.32. Now, are these the same? No, they're not exactly equal, but they're really, really close. And look, I told you to measure the nearest tenth of a Newton. This digit and this digit are approximations. They can be a little bit bigger or a little bit smaller than what was actually going on. This might have been 1.6, or it might have been 1.4, or somewhere in there. This is an estimate, and this is an estimate. And so when we do the product, and even these that might have little tiny variations or variation from what was actually written down. So it's actually pretty rare that the data measured like this are so perfect that you would get exactly the right. But how many, raise your hand right now if this product was the same as this product. Raise your hand. So I got 1, 2, 3 groups out of the 9. Raise your hand if this product here and this product here are very, very close. Now, what did you guys get? 2.7 and 3.2? Yeah. Okay, I think that's probably beyond what I would expect to have as error. So you might want to check that again. One of your scales might not have been zeroed or whatever. So you might want to try that again. Anybody else? Let's see, group 9, what did you guys get?
2.7 and 2.8.
2.7 Newton meters and 2.8 Newton meters. Yeah, that's really, really close. So what we can say this in terms of the magnitude, I'm going to write this on your paper. So anyway, is that R1 times F1 is approximately equal to R2 times F2. We have seen that. We've seen that here. And some of you applied greater or smaller forces, but the products will be very, very close to being the same, even if those products are different from the other groups. Okay, so come on up, get your notebook. Okay, so what we see is that R1 times F1 is approximately equal to R2, thank you very much, by the way, times F2. And in fact, if we had really much more precise measuring instruments and so on, this is true. This works. Now, we have a name for this force that makes something want to twist. We call it a torque. A torque. Now, the way we define a torque is this. A torque, oh, by the way, the variable we're going to use for torque is a tau. That is a Greek letter tau. And tau is going to be equal to R times F. What is R? We call R the lever arm. It's the distance from the axis of rotation to the application of the force, if those forces are perpendicular to R. Now, we'll get to we'll actually get a little more complicated here in a second. Okay, now, I want to talk about assigning a direction to the torque. Look at F2 here, R2, F2. What direction does R2 times F2 make the stick want to go in if you're holding it at the bottom? If you're holding it like this, but you took away F1 and you just pulled on the stick to the right, what's going to happen to that stick? It's going to what? It's going to go to the right? Be more precise, though. Is the whole thing going to slide to the right? No, you're holding it at the bottom. So guess what it's going to do? Because you're holding it, you're pinning it at the bottom. So rather than translate to the right, it's going to rotate. And I guess you could say, well, the top part's going to move to the right compared to the bottom part. It's going to rotate like that. But instead of doing that, what we're going to do, we're going to define that direction as being if it makes it want to rotate like this, we're going to call that the clockwise direction. It makes it want to rotate clockwise. Now, here's how we define positive and negative with clockwise, or what we're going to talk about counterclockwise. I'm going to zoom all the way. I guess I am zoomed out. Clockwise, everybody take your right hand right now. You can put your pencil down and take your right hand. You do this at home. Now I'm going to make my right hand rotate clockwise as F2 is trying to make this stick do. Clockwise. What direction is my thumb? If my hand curls in a clockwise direction, my thumb is straight down. So you hold your hand like this with your thumb perpendicular to your fingers, and you rotate your hand so that your fingers rotate in the direction the stick wants to rotate. My thumb is down into the paper. Thumb into paper. We're going to call that the negative direction. Now, counterclockwise, let's take a look at F1. F1 makes this stick want to rotate like this, opposite to the direction our clock moves. So that's counterclockwise. Now, if I take my right hand and I rotate my hand so that my fingers can curl in a counterclockwise direction, my thumb is straight up. And we call that thumb out of paper the positive direction. So in essence, R2, F2 is a negative torque, R1, F1 is a positive torque. But they're equal to each other in terms of magnitude. So when I add the two torques together, R1, F1, if I say R1, F1 plus R2, F2, when I do this using the right-hand rule, this quantity is going to be this quantity right here is going to be negative, but it's going to be the same value as this. So let's say, what was the one that we had? Actually, I'll use yours. You had 2.7
2.8.
or 2.8. I'll just say this is 2.8 Newton meters plus negative 2.7 Newton meters. Well, that's pretty close to being zero, right? It's 0.1, but because of our margin of error in our measurements and so on, this is an acceptable thing to say. So yeah, so the negative means counterclockwise, and that means, the negative means clockwise, the positive means counterclockwise. And that's just by convention. You know, a bunch of physicists got together and decided to do that. Now, last thing, what time's the bell ring? We're getting close. Okay, yeah, I got a few minutes. So, I'm going to come up with a slightly more general thing. Let's suppose we have a stick that's pinned like this. And I'll put it horizontally. We're not going to worry about weight right now, the weight of the stick. We'll do that later. But now, let's take a look at, what if I applied a force right here on the stick, and I applied a force like this? Is this force going to cause this stick to rotate? I mean, look, here's a pencil, and I'm going to pin it right here, and then I'm going to pull on it. No, it doesn't make the pencil rotate. Well, what if I took this and I applied a force like that? Is that force going to want to make it rotate? Oh, yeah. So I think you can see that it's the component of the force. Now well, let's think of these as components. This is the component that runs along the lever arm, and this is the component that's tangential or perpendicular to the lever arm. Okay? And so now if I add these two together, pick this up, put it right there. So here's my actual force. This is my force F. Now this is my lever arm. This is R. But what I'm going to do is I'm going to extend it out like this, and this is going to be my angle theta. And this part of the force that makes it want to rotate is this component over here, which is F sine theta. Okay? So the torque, if this is R, so the torque that makes things want to spin is equal to R, the distance from the axis of rotation to the application of the force, times the magnitude of the force, times the sine of the angle you get when you extend R out like this and you measure theta. And this is really the definition of torque. And you are going to solve a bunch of problems. Hey, you definitely, because we're a little short on time, you definitely need to read the book and solve the problems and so on. There's a few little odds and ends I didn't get to, but this is the gist of it. That is all.